Hello students, welcome to this lecture on circular motion which is given in chapter number 5 of class 11 physics. We have seen in chapter number 4 that acceleration of a body moving in a circle of radius r with uniform speed is given by v square by r directed towards the center. This force acts on the body along the radius and towards the center. According to the second law, the force Fc, that is force due to circular motion, providing this acceleration is Fc is equal to mv square by r. This force is also always directed towards the center and is called centripetal force. Some examples of centripetal forces are, which were given in chapter 4 as well, a particle tied to a string and whirled in horizontal circle, a vehicle taking a turn on the level road, a vehicle on a speed breaker, the revolution of Earth around the Sun, electron revolving around the nucleus in an atom, a charged particle describing a circular path in a magnetic field, etc. In this section 5.10, we will discuss two interesting cases, that is, motion of a car on a level road and motion of a car on a banked road. This is a very interesting topic. Please note down everything. In the end, we will solve some problems in mechanics and as well as few simple questions also will be solved. So I welcome you once again. Okay, first case is motion of a car on a level road. Please see the figure on the right hand side. The car is moving with a speed v in a circular path, and its acceleration is given by v square by r as shown in the figure. From the figure, three forces are acting on the car. The weight of the car, due to which that is mg. The m is the mass of the car and g is the gravitational force. And to counter this, there is one normal reaction n, which is perpendicular but opposite to mg. And in addition, there is a frictional force F. As there is no acceleration in vertical direction, n minus mg, that is vertical equilibrium of vertical forces, n minus mg equal to 0. That is n is equal to mg. Let it be equation 1. The centripetal force required for circular motion is along the surface of the road and is provided by the component of the contact force between road and the car tires along the surface. See, this is the contact between the tire and the surface of the road. This by definition is the frictional force. This F is frictional force. Note that it is the static friction that provides the centripetal acceleration. The static friction opposes the impending motion of the car moving away from the circle. Using equations which were derived in section 5.9, recalling Fs is less than or equal to mu s into n, where Fs is the static frictional force and mu s is the coefficient of static friction and n is the normal. And the second equation is Fc, that is force due to circular motion, is equal to mv square by r. We get the result, combining these two, we get the result F is equal to mv square by r, that is less than or equal to mu s into n. Or simplifying these two, v square is equal to cross multiplying mu s into n into r divided by m, or v square is equal to, substituting n is equal to mg, we get mu s into mg into r divided by m, that is equal to mu s into r into g. Therefore, velocity will be equal to square root of mu s into r into g, which is independent of the mass of the car. See, there is no factor of m in this equation, velocity equation. This shows that for a given value of mu s, that is coefficient of static friction and radius of the circle, there is a maximum speed of circular motion of the car, which is given by the relation V max, that is velocity, maximum velocity is equal to square root of mu s r into g. Let this be equation 2. Next we will study. Let us examine the case of a moving car on a banked road. The figure on the right hand side shows a car moving on a banked road. Banking of the road is done to reduce the friction, increase the speed, and increase the safety of the vehicle. The forces acting on this car are inclined force N, which is normal to the car and inclined at theta. This force N can be resolved into two components, N cos theta and N sin theta, as shown in the figure. So the second force acting on the wave car is frictional force F, which is parallel to the inclined road at an angle theta, and this can be resolved into F cos theta, horizontal component, and vertical component F sin theta. The third force acting downwards is due to the weight of the car and equal to mg. Resolving these forces acting on the car, we get N cos theta vertically upwards is equal to mg plus F sin theta vertically downwards. And horizontal components F cos theta plus N sin theta is equal to mv square by r. These are shown in the figure. We also know that F is less than or equal to mu s into n, where F is the static frictional force and mu s is the coefficient of static friction. Putting this value of F, we get in equation 3, we get N cos theta is equal to mg plus mu s into sin theta. And resolving for n, we get n is equal to mg divided by cos theta minus mu s sin theta. Again, substituting for f less than or equal to mu s into n, we get mu s into n cos theta plus n sin theta is equal to mv square by r. Substituting for n in the above equation, we get n is equal to mg divided by cos theta minus mu s into sin theta into mu s cos theta plus n sin theta equals mv max square divided by r. Simplifying, we get V max is equal to square root of R into G into mu s cos theta plus sin theta divided by cos theta minus mu s sin theta. Therefore, V max is equal to square root of Rg into mu s plus tan theta divided by 1 minus mu s tan theta. Let it be equation 5. Comparing this equation 5 with the equation for maximum speed in the case of a car moving on a flat road, we observe that the maximum possible speed of a car on a banked road is greater than that of a flat road. Suppose we put mu s equal to 0 in equation 5, we get V naught is equal to square root of Rg tan theta. There are certain important points regarding this equation. When the speed V naught is equal to square root of Rg tan theta, frictional force is not needed at all to provide the necessary centripetal force. Driving this speed on a banked road will reduce the wear and tear of the tires. This equation also tells us that for the value of V less than V naught, the frictional forces will be up the slope here, and that a car can be parked only if tan theta is less than or equal to mu s. In this section, we will solve some of the worked examples of circular motion. Question number 10. A cyclist speeding at 18 kilometers per hour on a level road, please note on a level road, takes a sharp circular turn of radius 3 meters without reducing the speed. The coefficient of static friction between tires and the road is 0.1. Will the cyclist slip while taking the turn? Answer. On an unbanked road, frictional force alone can provide the centripetal force needed to keep the cyclist moving on a circular turn without slipping. If the speed is too large or if the turn is too sharp or both, the frictional force is not sufficient to provide the necessary centripetal force and the cyclist slips. Hence, the condition for the cyclist not to slip is given by the relations V square is less than or equal to mu s into r into g, where V is the speed, mu s is the coefficient of static friction, r is the radius of the circular turn, and g is the gravitational force. And it is given in the question r is equal to 3 meters, g is equal to, we have to assume 9.8 meters per second square, and coefficient of static friction is 0.1. Therefore, substituting these values in the equation mu s into r into g, we get the answer 2.94 meters per second square. Therefore, V is equal to, it is stated that it is 18 kilometers per hour. So, converting this into meters per second, we get 5 meters per second. So, 18 kilometers turned into meters and per hour turned to seconds. Therefore, we get V square, squaring V square is equal to 5 into 5, 25 meters square per second square. Therefore, for safe driving, the velocity or speed, square of the speed should be less than or equal to 2.94 meters square per second. Whereas at 18 kilometers per second per hour, we get V square is equal to 25 meters square per second square. So that is not safe. So the condition is not obeyed. Cyclist will slip while taking the circular turn. Next question. Question number 11. A circular racetrack of radius 300 meters is banked at an angle of 15 degrees. That is, theta is equal to 15 degrees. If the coefficient of friction between wheels of a race car and the road is 0.2, what is the A? Optimum speed of the race car to avoid wear and tear on its tires. And B, question B is maximum permissible speed to avoid slipping. Answer. On a banked road, the horizontal component of the normal force and the frictional force contribute to provide centripetal force to keep the car moving on a circular turn without slipping. At the optimum speed, the normal reactions component is enough to provide the needed centripetal force and the frictional force is not needed. The optimum speed V0 is given by the relations V0 is equal to square root of R into G into tan theta, where V0 is the speed, optimum speed, R is the radius of the circular path, G is the gravitational force, and theta is the angle of inclination, that is banked rotor angle. Therefore, it is given R is equal to 300 meters, theta is equal to 15 degrees, and we have to assume G is equal to 9.8 meters per second square. Therefore, V naught is equal to square root of R into G into tan theta. Substituting the values and obtaining the value of tan 15 degrees from tables, we get V naught is equal to 28.1 meters per second. Therefore, the maximum permissible speed Vmax is given by the relation Vmax is equal to square root of R into G into mu s plus tan theta divided by 1 minus mu s tan theta. This equation we have derived in section 5.10.2, and substituting the values we get Vmax is equal to 300 into 9.8 into mu s is given as 0.2 plus tan 15 degrees divided by 1 minus 0.2 into tan 15. Obtaining the value of tan 15 from tables, we get the answer as 38.1 meters per second. That is the answer. In this section, we'll discuss about this, the method to solve problems in mechanics using free body diagrams. To solve a typical problem in mechanics, we should use free body diagrams and the following, which is made using the following steps. Step number 1, draw a diagram showing schematically the various parts of the assembly of the bodies, the links and support, etc. That is the first step, and this will be given by examples in the next section. Choose a convenient part of the assembly as one system and draw a separate diagram which shows the system and all the forces on the system by remaining part of the assembly. Include also the forces on the system by the other agencies. Do not include the forces on the environment by the system. A diagram of this type is known as free body diagram. Step number 4. In a free body diagram, include information about forces, that is their magnitudes and directions, that are either given or you are sure of. For example, the direction of the tension in a string along its length. It has to be marked. The rest should be treated as unknowns to be determined using laws of motion. The last and final step is, if necessary, follow the same procedure for another choice of system. In doing so, apply Newton's third law of motion. That is, if in the free body diagram of A, the force on A is due to B is shown as F, then the free body diagram of B, the force should be in opposite direction. That is, force on B due to A should be shown as minus F. Let us take up some examples. In 5.11, we will consider the acceleration of a block on a horizontal smooth surface. Case number 1. When a pull is acting at an angle theta to the horizontal, that is upward. Please see the diagram here. M is a body on a flat surface. Its weight is m and it is acting downwards mg. And the reaction is shown as vertically up. And the horizontal force F is applied at an angle theta here. And F has got two components, F cos theta horizontal and vertical component F sin theta. Therefore, equating the forces R is vertically up and F sin theta. That is R plus F sin theta is equal to mg. That is R F sin theta is upwards, mg is downwards. Therefore, rearranging R is equal to mg minus F sin theta and F cos theta is equal to ma. So, we have applied an acceleration. It gets an acceleration due to the force. It is ma. Therefore, a is equal to F cos theta by m. Next case, then we'll consider acceleration of block on a smooth inclined plane. Please see the diagram. The block in the previous case is on a inclined plane. Its mass is acting downwards mg and it is applied with a smooth acceleration a as shown here. And as usual, there is a reaction vertical and force F is there and mg is on the left side and mg cos theta is the vertical component. Therefore, when the inclined plane is at rest, the inclined plane itself is not moving, it is at rest. So, only body is moving. Then normal reaction R is equal to mg cos theta. So, vertical component, this is the mg acting downwards and this vertical component is mg cos theta. Therefore, force of the along the inclined plane F is equal to mg sin theta. Therefore, ma is equal to the acceleration ma is equal to mg sin theta. Therefore, a is equal to g sin theta. That is m and m gets cancelled. So, next case is when the inclined plane is given a horizontal acceleration b. So, in this case number 2, the inclined plane is given a motion by applying a force b, acceleration horizontal as shown here. This is force b. Since the body lies in an accelerating frame, the inertial acts as on it is in opposite direction. Normal reaction is equal to mg cos theta plus mb sin theta. And ma is equal to mg sin theta. Mg sin theta is in this direction and mb cos theta is in opposite direction. Therefore, m gets cancelled. A is equal to g sin theta minus b cos theta. Now we will consider some more free body diagrams of motion of blocks. Motion of block in contact, that is when two blocks are touching each other. Please see the diagram. Case 1. M1 blocks A and blocks B are touching one another. The weight of block A is M1 and weight of block B is M2. And the force is applied as shown in the diagram, that is from left to right in this direction of arrow. Now we draw this separately. The free body diagram of A as shown here in this yellowish color with a border. So applied force is left to right and the reaction is in the opposite direction. So the acceleration due to this F is m into A, which is from left to right. These please mark the arrows correctly. And the in free body diagram of B is shown here with the blue color. So it is this small f is due to friction, which is from left to right. Please see the difference here. In block A, it is from right to left in this direction of arrow. In the block B, it is left to right. So MA is in this direction of arrow. Let us write the equation. F minus F in the free body diagram, if you take the free FBD1, F minus F, because they are in opposite direction, is equal to M into M1 into A. So therefore F is equal to, from free body diagram 2, F is equal to M2 into A. Therefore we can write A as F. Solving these two equations, we get A is equal to F over M1 plus M2. So small f is equal to M2 into capital F divided by M1 plus M2. These are also by solving these equations. Now we'll take up case number 2 and see the diagram here. Here this diagram is same as the previous one, but here the direction of force is opposite, that is from right to left, capital F. Please see the diagram. So the free body diagram of A and B is written as earlier, but in this case the F is acting on B. So it is in right to left and friction is in the opposite direction, small f. Therefore, from free body diagram of A, that is 1, is F is equal to M1 into A. And capital F minus small f is equal to M2 into A from the free body diagram 2. Therefore, A acceleration A is equal to F divided by M1 plus M2. That is substituting and solving for A. And small f is equal to M1 into F divided by M1 plus M2. Please solve yourself, write and practice it, and you will become master over this subject. Then the next case is motion of blocks connected by a massless string. In the previous case, A and B were touching one another, but in this 5.11.3, the blocks are connected using a string. Please see the diagram here. Block A is connected to block B through a massless string. So it has got a tension T and force is applied in this direction, F, that is left to right. So free body diagram A is shown here and free body diagram of B is shown here. So we will write the equation. F minus T is equal to M2 into A. That is from this diagram, F minus capital T is equal to M2 into A, and T tension is equal to, from free body diagram, capital T is equal to M1 into A. So solving for A, we get A is equal to F divided by M1 plus M2, and tension is given by M1 divided by, substituting for A, M1 into F divided by M1 plus M2. The next case is the force is acting in opposite direction. Please see the diagram here. The force is acting on A from right to left, as in the direction as shown in the block diagram. So free body diagram is written here separately for A and separately for B, and its equations are F minus T is equal to M1 into A, T is equal to M2 into A. Therefore, A is equal to F divided by M1 plus M2, and capital T tension is equal to M2 into F divided by M1 plus F2. Please see the change in difference between T in the previous case as well as in this case. Please practice it again and again. Next is free body diagram of motion of three blocks connected with a string. This is also same as that, but we have to write three different free body diagrams of A here, B in this second one, and the third one is for C, and their equations are given here. So we write the equations, free body diagram separately. For A, F minus T1 is equal to M1 into A, and free body diagram of figure 2 body B is T1 minus T2 is equal to M2 into A, and free body from the free body diagram of C, it is T2 is equal to M3 into A. Please mark the directions of forces and tension very correctly, and solving, we get the values of A acceleration is equal to F divided by M1 plus M2 plus M3, and tension T1 is equal to M2 plus M3 into F divided by M1 plus M2 plus M3. T2 is equal to M3 into F divided by M1 plus M2 plus M3. You copy this diagram and write the equation leisurely and solve this. Next case is motion of connected blocks over a pulley. This is a special case, and here some uh, very serious thinking and very concentration is required. Please listen very carefully. Please see here, this P is a pulley which is attached to a ceiling, and it is connected, this pulley, at a string is passed over the pulley and weights are attached. A is attached on the left hand side with mass M1. On the right hand side we have B and C. B has a mass of M2 kg, M2, and C has a mass of M3, and its tensions are that when at the stationary point, T1 is equal to T2 and T3 is the tension acting upward. T1 on the left side, T1 is equal to T1 on the right hand side, and the tension between B and C is T2, and free body diagrams are shown on the right hand side. You please write down the free body diagram for A here, and for B it is here, and for C it is shown here, and for the pulley itself it is shown here. So pulley has got a tension T3 acting upwards, and its downward tension is T1, and T1 both are equal on the both sides. So its equations are free body diagram 1, M1A is equal to T1 minus M1G, and so we can calculate this T1. This is the answer. Tension is 2M1 M2 divided by M1 plus M2. This you have to solve after writing all the free body diagrams. So free body diagram of 2 is M2A equals M2G plus T2 minus T1, and then and T2, tension T2 here is 2M1 M2 divided by M1 plus M2 into G. So from free body diagram 3, M3A is equal to M3A acting downwards is equal to M3G minus T2, and for pulley T3 is equal to 4M1 M2 M1 plus M2G. See, the relationship or equation for tension you will get only after solving all the four equations, including free body diagram of 4, that is pulley. For pulley, T3 is equal to T1 plus T1, that is 2T1, that is T3 is upwards, T1 is downwards. Therefore, from this we can calculate A is equal to M2 plus M3 minus M1 into G divided by M1 plus M2 plus M3. From these four equations from free body diagram, you have to get the value of A, and then substitute the value of A in the respective equations to get the values of T1, T2 and T3. Next question. This is the case, next case. This is the case of a weight of a body in a lift. This is not included in NCERT portion, hence I will go fast. Only those of you who are appearing for competitive examination and some selected state boards have to go through this. So this is a special case. When a body of mass m is placed on a weighing machine which is placed in a lift, please underline the weighing machine is kept in a lift, then the actual weight of the body is mg. This acts on the weighing machine which offers a reaction R given by the readings of the machine. So you know that lift moves vertically up and vertically down. Hence the forces will be acting in different directions. The reaction exerted by the surface of contact on the body is apparent weight of the body. Please see different cases when lift is at rest, case 1, and lift is moving upwards, case 2, and lift is accelerating upwards at the rate of A, and then lift is accelerating upward at the rate of G, and lift is accelerating downward at the rate of A. Lift is accelerating downward at the rate of G. Then lift is accelerating downward at the rate of A greater than G. So the relationship of velocity, acceleration, reaction and conclusions are shown here. Those of you who are interested may go through in detail, otherwise a normal student may skip it. We'll continue our discussions with some of the numerical problems. Initially, we will answer short answer questions of 2 or 3 marks. Question 13. If the net force acting upon a particle is 0, show that its linear momentum remains constant. Answer. As force is proportional to dp by dt, that is change of momentum. When F is equal to 0, dp by dt is 0. Therefore, P should be constant. Hence, linear momentum remains constant if the force upon a particle is 0. Next question. A force of 36 dynes is inclined to the horizontal at an angle of 60 degrees. Find the acceleration in a mass of 18 gram that moves in the horizontal direction. Answer. It is given that F is equal to 36 dynes, which is acting at an angle 60 degrees. Therefore, Fx, that is the force along x-axis, is equal to F cos theta, that is F into cos 60. So, if we take the value, it is 18 dynes, because cos 60 is half. So, 36 into half is 18 dynes. Fx equals m into ax. We know Fx is equal to mass into acceleration. Therefore, ax is equal to Fx divided by m, that is equal to 18 by 18, that is equal to 1 centimeter per second square. Next question. The motion of a particle of mass m is described by the equation h is equal to ut plus half gt square. Find the force acting on a particle. We know that it is given h is equal to ut plus gt square. Therefore, velocity v is equal to dh by dt. So we have to differentiate this equation 1, that is equal to d by dt of ut is u plus d by dt of half gt square is gt. That is 2 into half gt, 2t into half gt is gt. Therefore, again differentiating, we get a is equal to dv by dt, where v is the speed, velocity divided by dt. That is equal to, differentiating, we get a is equal to g. Therefore, F is equal to m into a. So, substituting the value of a equals g, we get F is equal to mg. Next question. A particle of mass 0.3 kg is subjected to a force of F is equal to minus k into x, with k is equal to 15 Newton per meter. What will be its initial acceleration if it's released from a point 20 centimeter away from the origin? As F is equal to ma, we know that F is equal to ma and k is equal to 15 Newton per meter and x is equal to 20 centimeter, it is given. Therefore, F is equal to minus Kx, that is equal to m into A. Therefore, substituting the values, A is equal to Kx divided by N between these two relations. Therefore, A is equal to 15 into 20 divided by 0.3, that is equal to 10 meters per second square. That is the answer. Therefore, A is equal to minus 10 meters per second square. Question 16. A 50-gram bullet is fired from a 10 kg gun with a speed of 500 meters per second. What is the speed of the recoil of the gun? Therefore, initial momentum equal to 0. Using conservation of linear momentum, we know that mv plus capital MV equal to 0, where small m is the mass of bullet and v is the velocity of bullet, m is the speed of the gun, and v is the velocity. Therefore, v is equal to minus mv divided by capital M. That is equal to, substituting the values, v is equal to small m 50 grams of bullet into velocity of bullet is 500 meters per second, it is given, divided by the weight of the gun is 10 kg. 10 kg converted into grams is 10,000 grams. That is equal to, simplifying, we get 2.5 meters per second. The minus it seems the velocity is in opposite direction. Question number 17. A bob of mass 0.1 kg hung from the ceiling of a room by a string 2 meter long is oscillating. At its mean position, the speed of bob is 1 meters per second. What is the trajectory of the oscillating bob if the string is cut when the bob is number 1 at the mean position and 2 at its extreme position? Therefore, at its main position, its trajectory is parabolic, and at its extreme position, it is vertically downwards. Next question. What is the acceleration of the block and trolley system as shown in the figure? If the coefficient of kinetic friction between the trolley and the surface is 0.04, also calculate the friction in the string. Take G is equal to 10 meters per second square. Mass of string is negligible. Please see the figure. Here trolley is weighing 20 kgs and the weight of the block is 3 kgs. And it is connected through a string of tension T, and mu K is the friction, coefficient of friction. And the free body diagram of 3 kg weight is shown here in the diagram. So 30 minus T equals 3A. Mass is 3 kgs and A is acceleration minus 10. 30 newtons is downwards and T is upwards. That is equal to 3 into A. Free body diagram of trolley is shown below. It is 20 kg. Hence, the mass into acceleration, the force is 20 into A, acceleration, and Fk is the friction, kinetic. Fk is the force due to friction and T is the tension on the right hand side. Hence, its equation is T minus Fk is equal to 20 into A. Let it be equation 2, where Fk is equal to mu k into N, that is equal to mu k, coefficient of friction, is given as 0.04 into 20 newtons into 10, that is equal to 8 newtons. Solving 1 and 2, we get A is equal to 0.96 meters per second square and T is equal to 27.2 newtons. Next question. A spring balance is attached to the ceiling of a lift. When the lift is at rest, spring balance reads 49 newtons of a body hung on it. If the lift moves downward and upward and with an acceleration of 5 meters per second square, and then the third case is with a constant velocity, what will be the reading of the balance in each case? We have introduced the concept of mass kept in a lift in the previous slides. So the same thing we are solving in a problem. Therefore, reaction is equal to m into g minus a. Therefore, weight is equal to 49 newtons. Therefore, m is equal to force by acceleration. Therefore, 49 by 5 is equal to mass, we have found it as 5 kg. Therefore, R is equal to 5, that is mass, into 9.8 minus 5. This 5 is acceleration, meters per second square, and this 5 is 5 kgs. Therefore, R is equal to 24 newtons. Second, case number 2. R is equal to m into g plus a. R is equal to 5 into 9.8 plus 5. These formulae g plus a is all given in the previous slides. Therefore, R is equal to 74 newtons. Case number 3. As A is equal to 0, that is when the lift is moving with a constant velocity, acceleration is 0. So R is equal to m into g, that is equal to 49 newtons. That is the answer. So next question. Question 20. Define force of friction. How does ball bearing reduce the friction? When two bodies are in contact, each experiences a contact force of the other. Friction is defined as the component of contact force parallel to the surfaces in contact, which opposes the impending or actual relative motion between the two surfaces. The contact area between the ball bearings and the surfaces is very small. Hence, the rolling friction is reduced. That is the answer. In this video lecture, we have studied theory about circular motion and how to solve problems in mechanics. We have also studied about free body diagrams, and some typical questions also have been answered. In the next session, we will summarize the entire chapter 5 and do all the remaining problems. Till then, goodbye.